Hi, this is a video lesson on section 9.1 sequences. We start off by reminding ourselves that a sequence is a list of numbers written in an explicit order. It is also a function with domain, the set of positive integers. And so, an infinite sequence has an infinite number of terms. The 1, 2, 3, that's what you see there. Those are the quote-unquote inputs, or the domain. And that's why the domain is a set of positive integers. A sub 1, A sub 2, A sub 3, A sub 4. A finite sequence has a finite number of terms. So A sub n is a sequence that has terms A1, A2, A3, all the way to A sub n. Explicit formulas are really easy to work with. To find the very first term for this first example, all you have to do is put in 1 for n, and you get 6. To get the second term, all you do is put 2 in for n, and you get 18. To get the third term, you plug 3 in for n, and you get the third term. The beauty of an explicit formula is that you can get any term. So if I want the 100th term, I would only have to put in 100 in for n. The second example here, if I want to get the first term, I plug in 1 for n, and that will give me negative 1/3. If I want the second term, I will plug in 2 in for n, and that will give me positive 1/5. The third term would be plugging 3 in for n, and that will give me negative 1/9. And the fourth term would be plugging 4 in for n, and that will give me positive 1/17. Take a look at what's happening here. This expression up here, negative 1 raised to the n power, that expression alternates the sign of the terms. So in this particular case, the first term is negative, the second term is positive, the third term is negative, fourth term is positive, and so on and so forth. So if you see an expression like this, it alternates the sign of the terms. Recursive formulas are also really helpful. What the recursive formula does is that to get the nth term, you have to take the previous term and add 5 to it. So A sub 2 is going to be A sub 1 plus 5, and A sub 1 is 4, so 4 plus 5 is 9. A sub 3 is going to be A sub 2 plus 5, and A sub 2 is 9, so 9 plus 5 is 14, and so on and so forth. And so the recursive formula uses the previous term to get a particular term. Okay? And so in this second example, A sub 2 will be negative 2 times the previous term, which is 3. A sub 3 would be negative 2 times the previous term, which is negative 6, giving us 12. And A sub 4 would be the previous term, or negative 2 times the previous term. So that would be 24. Moving on, here's a quick review of factorial. Factorial, n factorial, is the product of all positive integers from n down to 1. So 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. 18 factorial is 18 times 17 times 16, all the way down to times 3 times 2 times 1. And so n factorial will be starting with n, multiplied by the integer right before n, which is n minus 1, multiplied by the integer right before that, which is n minus 2, so on and so forth until you get to 3 times 2 times 1. And so in this first example, it says find the first 4 terms of this. So A sub 1 will be 1 plus 1 factorial over 3, 2 factorial over 3. So 2 factorial is 2. The second term is parentheses 2 plus 1 factorial all over 3. 3 factorial is 6, so that's 6 over 3. Okay? A sub 3 is 3 plus 1 factorial over 3. 4 factorial is 24, so that's 24 over 3, 8. A sub 4 is 4 plus 1 factorial over 3. 5 factorial is 120, so that's 120 over 3, which gives you 40. And so now, let's simplify expressions with factorials in it. 25 factorial is 25 times 24 times 23 times 22 times 21, all the way down to 3 times 2 times 1. 23 factorial is 23 times 22 times 21 times all the way down to 3 times 2 times 1. As you can see, everything 23 and below cancels, giving you 25 times 24. Okay? And 25 times 24 is 600. All right, I'm going to go straight to D. Part D, n factorial is n times n minus 1 times n minus 2 times n minus 3 all the way down to 3, 2, 1. And n minus 1 factorial is n minus 1 times n minus 2 times n minus 3 all the way down to 3 times 2 times 1. As you can see, everything cancels but n. Now let's review summation notation. This is something that you should already know. 2i with I starting at 1 and going to 8. That means 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4 all the way to plus 2 times 8. Okay, so going down to part E, when I is 1, the expression 4 is just 4. When I is 2, the expression 4 is just 4. And so it looks like all the time the expression is 4, and we have 50 of these. And so the answer here is 4 times 50, which is 200. Okay, now we go in reverse. I give you a sum written out, and you have to write it as in summation notation. And so what you have to do is you have to look for a pattern. So the pattern for part A is that this is 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, all the way to 2 to the 10th. So this one is going to be 2 to the k power, k starting at 1 and ending at 10. Okay, you could also write this as if you want to start off at k with 0. If k starts at 0, then it ends at 9, and in this case, it will be 2 raised to the k plus 1 power. Okay? All right, look at part B. Part B, the signs alternate. And so to create that, all you need is a factor of -1 raised to the n plus 1 power. Because the first term is positive, the second term is negative, the third term is positive. So if I want the first term to be positive, I need the first time this exponent appears to be even. So I can make n equal to 1, and this is 1 plus 1. And then this is, the pattern is, these are also powers of 2. So we're going to have 2 to the n minus 1 power in this case. Okay? And so then this goes up to 11. Okay? All right. There are different ways of writing this. So this one, part B, you could also write this with n starting at 0 and ending at 10, in which case it would be -1 to the nth times 2 to the nth power. So there are always multiple ways of writing these things. Even this second one can be written like this. Since they're both raised to the nth power, you can write it as -2 to the nth power. Okay, now let's talk arithmetic sequences. Arithmetic sequence is a sequence in which each term after the first differs from the preceding term by a constant amount, called the common difference. So here, as you can see, to go from one term to the next, you add 3. So the explicit formula is a sub n equaling the first term, 2, plus n minus 1 times the common difference. The recursive formula always starts by you writing the first term, and then all subsequent terms is the previous term plus 3. And so in part B, the common difference is a negative number because this time you are subtracting 5. So then the first term is 12 plus n minus 1 in parentheses times the common difference, which is negative 5. The recursive formula here is a sub 1 is 12, and a sub n is going to be the previous term, a sub n minus 1, subtract 5. So the general formula for an arithmetic sequence is a sub n equaling a sub 1, the first term, times parentheses n minus 1 times d, where d is the common difference. Okay, next we have geometric sequences. This is when each term you have to multiply by the same number to go from one term to the next. So here the common ratio is, for example, 1 here is 3 times 3. Here's the explicit formula from from pre-calculus honors and algebra 2. A sub n equals to the first term times the common ratio raised to the n minus 1 power. Okay? The recursive formula is a sub 1 equals to 2, and a sub n will be 3 times the previous term, which is a sub n minus 1. Okay? This one, the common ratio is 1/2. So the explicit formula is a sub n times the first term times 1/2 raised to the n minus 1 power. The recursive formula is write the first term, and then all subsequent terms are 1/2 times the previous term. So the general formula at the bottom of this page will be a sub n equals to a sub 1, which is the first term, times r, the common ratio, raised to the n minus 1 power. Next, we look at how to graph a sequence. Graphing a sequence is just like graphing any graph, except for one key difference. So I'm going to label this horizontal axis the n-axis. And if you remember, the definition of a sequence is a function that only has positive integers as inputs. And so when when n is 1, we have -4. When n is 2, we have -1. When n is 3, we have 2. When n is 4, we have 5. And the key difference is that we do not connect these points. This is a discrete graph, meaning that it is not continuous. There's no such thing as term number 1.5. And so it's only these isolated dots. Notice that these dots will continue to go up forever. Let's look at this second example. When n is, let me label 1, 2, 3, 4 on the horizontal axis. All right. When n is 1, we have -1/3. When n is 2, we have +1/5. When n is 3, we have -1/9. When n is 4, we have +1/17. Notice that this graph, these dots, alternate between negative and positive, but also gets closer and closer to 0 the higher that n is. In fact, we say that a sub n converges to 0 because the outputs are getting closer and closer to 0 the larger n is. This brings us to finding the limit of a sequence. All right, so a sequence converges if the limit of the sequence as n approaches infinity equals to L, where L is a constant. So basically, to see if a sequence converges, we take the limit of the explicit formula. In this case, in example A, the limit is infinity. Infinity is not a constant, so we say that this sequence diverges. Let's look at part B. We're going to take the limit as n approaches infinity of this explicit formula. And this is one where the denominator dominates. And so the limit is 0. So a sub n converges, and it converges to whatever the limit is, and so it converges to 0. In part C, the limit as n approaches infinity of this expression is negative 2/5. So this sequence converges to negative 2/5. What that means is that as n gets bigger and bigger, the sequence, the terms get closer and closer to negative 2/5. Finally, we have something called the squeeze theorem for sequences. If you have the limit of a sequence A and a sequence C that's both limits will be L, that means that these two sequences both converge to L. Then if you have a sequence that lies between those two sequences, then that middle sequence will also converge to L. And so here, I want to show what this sequence converges to. Well, take note that cosine is always between -1 and 1. And so what we can do here is we can take this sequence and squeeze it between -1 over n and 1 over n. Now this, if I take the limit as n approaches infinity, this limit will be 0. If I take this limit over here, n approaches infinity, this will also be 0. Well, the squeeze theorem then says that the limit of this middle sequence, and we know that this sequence is always in the middle because cosine is always between -1 and 1, we can then conclude that this limit is also 0, which means that this sequence, a sub n equals to cosine n over n, we say that it converges to 0. That's all, folks.